Hey there, welcome back. So we're going to pick up at number 2 on section 4.3, and we're going to do some more sketching to see how we're doing with all of that notation and figuring out our intervals of increasing, decreasing, and concavity. So on this page, you're actually given the information already. You don't have to solve the polynomial like we did in number 1. So we have all the information, so let's go through that first and see if we understand what it's telling us, okay? All right, so first off, they're telling us that f of -1 is 2 and f prime of -1 is 0. So let's talk about that. This is an ordered pair, right? The function value, that's an ordered pair. So we know that -1, 2 is on this graph, okay? -1, 2, that's a point. Now, what does this tell us about the point at -1? So at the first derivative of -1 is 0, that means this is a possible max or min. Okay, it's a critical value. It's definitely a critical value where the first derivative equals 0, right? Those are your critical values. So they could be a max or min. Remember, the only way we know that is how it changes from increasing to decreasing or decreasing to increasing. So that's what's coming up here. So let's see what this says. The first derivative is less than 0 when x is less than -1. So what does this tell you? Increasing or decreasing? Where the first derivative is less than 0, that's where the function is decreasing, right? That's where f of x is decreasing, okay? And it's decreasing to the left. X is less than -1. So at -1, that's a boundary. So right here is a boundary for me. Okay, and to the left of it, I know it's decreasing down here. Okay. All right. Part D says the first derivative is greater than 0. Well, wherever the first derivative is greater than 0, that's where the function is increasing when x is greater than -1. So on the right side of my dotted line over here, we're increasing. So all of this stuff over here is increasing from this dotted line over, not from 0, but from the dotted line. And then part E says the function second derivative is greater than 0 for all x. So what does this mean? This means the function is concave up, right? Greater than 0 is concave up everywhere, okay, for all x. So there's no boundaries. So that means it's concave up over here and here. We have to go through this point, and on this side we have to be decreasing and concave up. Remember, concave up is this. So this is the decreasing side of concave up. This is the increasing side of concave up. So right there, decreasing concave up till we get to that point. And then on this side, we've got to start increasing, but we're still going to stay concave up. Okay. So there's your graph. That's the info that got us there. So we knew nothing about the function. We just got stuff about the derivatives. So it's kind of cool how the derivatives help us figure out what the actual original function looks like without even knowing what it was. Okay. So again, we don't know every single thing, but this is just kind of, we're learning how to sketch and we're learning about the characteristics. Okay. All right. So that one was kind of pretty straightforward, but that's a good way to start to make sure you're okay with everything. So this is why I said it's real important what you know what these things are telling you about the graph. All right, so we need boundary points. So remember, the boundary points are going to come from what they're giving you in the information. You might be given ordered pairs, and then you might be given possible max or mins or possible inflection points. So this happened to be a minimum, okay? So over here, all I knew at the beginning that it could have been a max or min. I didn't know what it was until I got the rest of the information. But now that I'm looking at the graph, I can definitely see that that is a local minimum. Okay, it's down at the bottom. All right, let's try number 3. Same thing. Let's see if I can get them all on here. There we go. All right, so look at all of these in part A. These are all ordered pairs. They're function values. There's no little derivative signs. So these are all points on my graph. So I'm going to go ahead and plot the 0, 5, okay, 4, 5, 2, 1, and 3, negative 2. Okay, all points on my graph. So please make sure you understand if there is a derivative sign, that's not a point. That's telling you these are your possible max and mins. These are critical values. Okay, so if these in part B are critical values, okay, that means at x equals 0 and x equals 3, the x values, those are your possible max or mins. We don't know yet what they are, okay? But those are the only places where we could have a max or min based on this information. All right, so let's just write what this stuff means before we look at it. So f prime of x is less than 0. Remember, that means where the function is decreasing, right? Decreasing. First derivative greater than 0 is where the function is increasing. Second derivatives equal 0. These are hypercritical values. Right? So that means at x equals 0 and at x equals 2, those are possible inflection points. Don't know yet. Okay? All I know is it's possible. Until I get this graph done, I don't know that. But those are the places. Okay? Now, if 0 is a possible inflection point and a possible max or min, typically it's going to be this, if anything, but it might be. So let's just see. Can't be both, right? Cannot be a max or min and an inflection point. That's impossible. But we can see if it's one or the other. All right. Then we've got the second derivative less than 0. So less than 0 is where the function is concave down. And where the second derivative is greater than 0, I'm going to write this over here, or x is greater than 2, because that's kind of weird right there. Okay, just so that all goes together. So this is where your function is concave up. Okay, where the second derivative is greater than 0. So just kind of going through to tell you what we have. Now let's look at our boundary points. So anywhere on here is a boundary. So we've got between less than or equal to less than or greater than 3. So 3 is a boundary. We've got between 0 and 2. So those are boundaries. And then here is 0 and 2. So we have boundaries at 0, 2, and 3, it looks like. So it's hard to do 0 as a boundary. But so here's a boundary. 0. 2 is a boundary. And 3 is a boundary. 4 is not mentioned anywhere on my boundaries. So, right, I got less than 3, greater than 3. That's a boundary. I've got between 0 and 2, boundaries. I've got less than 0, boundary. I got greater than 2, boundary. Nowhere in here is 4, a boundary. So these guys, this guy is just a point on the graph. Okay? All right, so now we're going to start marking our arrows and our cups. Okay? So let's start with decreasing. We're decreasing less than 3. So everywhere less than 3, we are decreasing. So decreasing, decreasing, decreasing. Everywhere less than 3. So here's our boundary at 3. So everything, any other boundary in here is decreasing. We're going to be increasing greater than 3. So only over here are we increasing. All right, now we're going to do our concavity. Concave down came first. A lot of times they switch these, so just pay attention. Less than 0 is concave down. So we're concave down between 0 and 2. Between 0 and 2, we are concave down. 0 and 2 is right in here, so concave down this way. Okay? That's it for that one. And then concave up less than 0. So over here, we're concave up. and greater than 2, we're concave up. So that's in here and in here, because both of those are greater than 2, right? So I hope this is making sense to you, how we're doing that. All right, now we have to draw this graph, but we also have to go through these points. So that's why we got to do the points first, so we kind of know what we're doing. So I have to decrease concave up. So remember, decrease concave up looks like that. And I got to go through this point. So I got to start up here. So we're going to decrease concave up like that. And I got to hit that point. Now I'm going to stay decreasing, but I got to change to concave down. So remember, concave down, decreasing will be this side. So decreasing, because here's concave down. Increasing, decreasing. So I got to decrease and be concave down till I get to this point. Okay. Okay. Now I'm going to stay decreasing, but I'm going back to concave up, which is this. Decreasing concave up from here to here. So decreasing concave up. Okay, that's this piece. And lastly, concave up and increasing is this, right? Increasing and concave up. So I gotta go through this point, so it's gonna be pretty skinny. It's gonna be like that. Okay? All right, now I can't check this on my calculator, and this is typical for what you would get, because obviously if you can graph, you can easily sketch a graph without all this information. Here, you can't sketch the graph because I don't have the function to put in my calculator. So we're just sketching based on what is given to us, okay? So this is one of those things where once you get it, you will get it. But if you're struggling right now, don't panic. Just, you can, print out another blank sheet or write these problems down separately and try them again. But eventually, you're kind of going to see there's only so many things that can happen based on our first and second derivatives, okay? So you just have to get that down, and then the rest should become pretty, you just follow along once you have that, okay? All right, let's go to the last page then and look at number 4. 4 is true and false. These are my favorite kind because you really got to think about this. So consider the graph of the function below. Are each of the statements true or false? Okay. So let's talk about, if you know what this means, then these are really easy to do. So what does it mean if f prime of a number is 0? That's a critical value, right? So that means this is a possible max or min. Okay? I don't know if it is yet, but that's what that means. Possible max min. Okay? When a first derivative equals 0, that's a critical value, means possible max and min. Where the second derivative is less than 0, that means the function is concave down. Okay? I mean, there's only 2 things for each that we got to know. All right, so we're looking at -5. So at -5, is it a max or min? And is it concave down? Well, where's -5? -5 is right here. It is a minimum, so this part is true, but is it concave down right here? This part of the graph is concave up. So this is false. So if one of them is false, the whole thing is false. Okay, so this was okay, but that's why it's false. This is concave up right here. All right, let's do the same thing at B. This is a possible max or min. This is a possible inflection point, right? Where the first derivative equals 0, those are your critical values, possible max and mins. Where the second derivative equals 0, those are hypercritical values, possible inflection points. So let's go to -4 right here. It is an inflection point. It changes from concave up right here, and then it starts concave down. So that's an inflection point. So this is true, but it is not a max or min, okay? So that is the false part. So this is false. All right, part C. What does this mean? First derivative greater than 0, that's where the function is increasing. First derivative is increasing, decreasing. Second derivative is less than 0, that's concave down. Okay, so is that true at -3? So let's go to -3 right there. That is a maximum. It is not increasing or decreasing. It's a max. That means the first derivative equals 0 right there. First derivative equals 0 here and here on this graph. Max and mins are critical values. So this is not true, but it is concave down right there. That is true, concave down. But so that part. So one of these are true, one of these are false currently. All right, maybe part B will be true. Let's try that out. Okay, we're going back to -4. We already had a false statement at -4, so let's see what this one says. First derivative of -4 is greater than 0. That's increasing. First derivatives. Second derivative equals 0. That's a possible inflection point, right? Possible inflection point, because that is a hypercritical value. So let's go to -4. Right there. It's an inflection point. We already said that earlier. So this part is true. And look, it's on an increasing part of the graph right there. So that is also true. So we finally got one true one. Okay. So use your knowledge of this. It's kind of the way I look at it. Then look at the point. Okay. So that's good practice to do stuff like that. All right. 5 and 6 we're solving for a variable in a polynomial. And so this is what's important, is that you're understanding what is given to you. So number 5 gives you a polynomial and says it has a max at some value. Number 6 gives you a polynomial and tells you you have an inflection point at some value. So that's different, okay? This is first derivative, this is second derivative. All right, so if it has a max at x equals 0, that means f prime of 1 equals 0, okay? That's what that means. If you have a maximum at a value x, then the critical value was 0. So the first derivative at 1 would be 0. So we're going to use that when we get to the first derivative. So we're going to find the first derivative of this function. Now s is just a constant, so we're going to just multiply. So just like if that was 3, we would do 3 times 2. So here we're going to do 2 times s, okay, to find the derivative. So 2 times s is 2s, subtract 1 from the exponent. And then 6x is linear, so derivative of that is just 6. Derivative of -3 is 0. All right, so now we know that 2sx plus 6 has to equal 0 for critical values. And we know we had a critical value at x equals 1. So we can put in a 1 here because we know that equals 0. So if we put in 1 here, we can solve for s. Okay? So at x equals 1, the critical value was 0. So we're just going to solve that. So 2s times 1 is 2s plus 6 equals 0. Subtract 6 from both sides, divide by 2. So we get -3. So there's your value for s. So that's first derivative because max and min. Now, we're going to do the same thing for number 6, except it's an inflection point. So we have this function. It has an inflection point at x equals 3. Well, that means not f prime, but f double prime at 3 equals 0. So if f double prime at 3 equals 0, then I got to find the second derivative. Inflection points are all about the second derivative. So in order to find the second derivative, I got to find the first. So let's find the first derivative. 3 times 5 halves is 15 halves. Subtract 1, so that's x squared. Again, 2 times s is 2s. Subtract 1 from x, you get x. And the derivative of -6x is -6. Derivative of 1 is 0. Now we got to find the second derivative. All right, so 15 halves times 2 is 15x, subtract 1. Derivative of 2sx is 2s, right? That's the linear term. And then this is 0. All right, so again, I know that 15x plus 2s has to equal 0 at all hypercritical values. And because x equals 3 is an inflection point, it is hypercritical. So that means when x is 3, we know this is true. So 15 times 3 plus 2s has to be 0. So that's 45 plus 2s. So 2s equals -45. So s equals -45 halves. Okay. All right. Okay, so that's the end of that. So there's, these are important that you understand again what this means, okay? But big time in this section is about curve sketching and understanding the difference between critical values, what they are giving you, and the hypercritical values, okay? All right, so work on the homework. I'm here if you need any help, and I'll see you back here next time.